Right, on to isomerism.
Something mostly new, yeah?
Mostly new.
Dirty blue.
First, right, two different types of isomerism.
Yes, there is. We'll divide it up completely on the board. We've got structural.
And we have stereo. It's sensible to first say also what isomerism is.
Yes. It's where compounds have the same molecular mass. Remember, molecular mass being the actual number of atoms in a molecule.
But a different structural formula.
And that means a different arrangement in space for your marking points in an exam.
Yeah. So there's lots of different ways of doing this. There's already two main ways, but there's quite a few different ways of structural.
Yes, so I'll go for that first.
Okay.
I'll underline that because that is the title of this baton.
Alright, I'll do this one. So if we have something like butane...
I'm not going to draw all the hydrogens on again, so I'm trying to do this quick.
Yep. There's different ways of writing just this chain. You can have a side chain in the middle, and although it be a different structural formula or a different arrangement in space,
it will still have the same molecular formula.
Yeah. It's still the same amount of carbon, still the same amount of hydrogens as it was before.
Similarly, if you have an actual side chain, let's use OH because it's nice and simple. We'll use butane again.
So an OH
group. That can move just like the carbon did.
That can move to the middle. And that's another type of isomer, as it is the same molecular formula.
Yes. And finally, when you introduce double bonds, this one's a bit harder to get your head around, perhaps.
Yeah, maybe a little bit, but it's still okay. So you have maybe double bond on the last two.
Again, it's 4 carbons. I'm trying to do this nice and simple. You can imagine this carbon comes down here and this carbon comes up here, whereas in this one it's a 4 carbon chain.
The next one is a 3 carbon chain, so change in chain length would be another type of isomer.
With the same molecular formula, that's what it means. These are all structural.
Yep, here's
the structure's changing, but it's the same thing.
Now the second type, which is stereo. There's two types of stereo.
One of them isn't introduced until your A2
you
course.
You just need to know that there is two and it's optical.
Optical.
In case you want to read it up, but...
You don't need to know.
No, one we do need to know is EZ or cis-trans.
Yes, and that's where you have a double bond.
Something you should know about double bonds is they can't twist.
They can't rotate at all. You can't twist. If we have this one nice and simply, carbon to carbon, you have 2 chlorines on them and 2 hydrogens on them. You could draw this in another way. We'll draw that before explaining how you can't twist and orientate. You can have the chlorine at the top on this side and at the bottom on the other side. Now, because the double bonds can't rotate, there is no way of, if you imagine puffing this up and grabbing it, twisting it into
You can't change that into that. But they are the same molecular formula.
Yes. Now which one's cis and which one's trans, and how do you remember it?
Well, Wayne, I remember cis like sisters, so they like being on the same side. So this one would be cis.
And trans, I like to remember as transforming across the double bond.
Yeah.
You go there,
and you go across.
Across and up.
And when you talk about EZ, it's actually the opposite way around that we first said.
Yes.
So this one's Z and that one's E.
Yes, which is a bit confusing.
It's a bit confusing, but
that's isomerism.
That is.
2 different types and the different examples. It's hard sometimes to notice in question papers what's going on and which type of isomerism it is.
But
especially if it's this one, which contains a double bond, but isn't quite like this. This is a special type.
With practice it becomes more clear. So
let's move on to the next thing, is special types of reactions.
Alright, let's do that.
Hello! So we're going to go on to the different types of reactions now. This is entirely new above GCSE, but hopefully you've done
not
it before.
New for you. Yeah, so different types of reactions.
Homolytic and heterolytic. I'll write both of these up.
Okay.
Before we...
In 2 colours, I think. We have one blue, one
green.
Red.
Oh, red.
Yep. And heterolytic this side. You want to divide them in.
Okay, I like that idea. Now, it's all to do with the breaking of covalent bonds. That's what these 2 different reactions are all about. Which one should we do first?
I think we should do homolytic first. Yeah.
Homolytic is where the thins are the same. So if we have
homolytic
X to Y, and this is a covalent bond.
Yeah.
When the covalent bond breaks, to make them both the same, they must each take, so a covalent bond is a shared pair of electrons, they must each take one of these electrons to make them the same.
So if you draw the electrons on in the bond.
There'll be 2 electrons in the covalent bond, like Triv's doing here.
And one would go this way.
And one would go that way.
One would go that way.
This would make something called radicals, and it would make an X radical and a Y radical in this case. Like this.
Yeah.
and that is homolytic reactions.
We'll go on later on what these radicals actually do.
Yeah, but first we'll just explain them. So we've got heterolytic.
So, like before, if we have
an X and Y with a covalent bond,
yeah,
heterolytic means different. So they can't each take an electron like here. If we draw the electrons in, I'll draw it in blue because he did it on red on my blue.
they both go to 1.
They both go to 1, like this.
Now, instead of making 2 radicals,
They make 2 ions of opposite charge.
they do
The one that's gained 2 electrons, because electrons are negative,
a
isn't it?
negative charge.
That'll be-
So X will be positive.
And Y will be negative. I've put a plus in here because it makes both of those things, yeah. And these are the 2 types of reactions. And then we have some more new words above GCSE.
We do, we have electrophile.
And nucleophile. I'll do nucleophile.
Alright.
That's the new thing then.
Electrophile. So first, what a nucleophile is?
Yes. No, nucleophile isn't one thing. It could be lots of different atoms or molecules.
It's just a
It's
thing
just a
with
thing
a
to
property.
describe them, yeah. So a nucleophile is something that will attack an electron deficient carbon atom.
Basically, it's something that has a lot of electrons.
Yes, so it's normally a negative ion,
Yeah.
or it could be something with lots of lone pairs, but basically something that has electrons to give.
Yes.
It's got too many.
So it tries to attack places that are no enough.
Yeah. So ions that are negative and stuff with lots of lone pairs, and then electrophile.
Pretty much the other way around.
That's the opposite of that, yeah. Stuff that doesn't have enough, essentially.
Yeah, so it's like it is electron deficient. We'll try and find somewhere like a nucleophile
Yes.
to go.
Yeah, because stuff positive ions that have 1 less or even 2 less electrons than they should will try and
They
get
want
the
to have the
electrons.
full octet and be stable.
Yes.
So-
So now we'll actually go on to the reactions using these 2 types of fission, which is something new again.
Alright.
But we'll do that in the next take.
Okay.
Wait.
Hello! Now on to reactions we talked about earlier.
Yes, so first in the book is addition reactions.
It is.
Do it in blue.
Addition is when something's added. Makes sense. What we're going to have is we're going to have ethene and we're going to add a halogen to it. We're going to add bromine.
I like bromine.
I like bromine. Not going to put a hydrogen on. That'll take so long.
Yes.
So, Wayne, how do you do this?
Well, Triv, the double bond is actually made of a sigma and a pi bond. This is something you need to know. Now, the sigma bond is what's in single bond, so that's not broken. So it's the pi bond that is broken. And then we simply get this Br2, 2 Br molecules, 1 on one carbon, 1 on the other. Quite simple.
And again, not drawing on the hydrogens.
Not drawing on the hydrogens again. Now we do this mechanism, the actual proper mechanism for how this works, in part 4.
Yeah, because it's spread out in the book quite a bit.
Yeah.
Now we're on to substitutions.
Substitution first, yeah.
Alright, so let's do that.
Alright. Do it down here.
Substitutions when something's swapped. So we're going to swap a few things. We're going to have a halogen alkane. We're going to use bromine again, so why not? And we're going to add an OH minus to this one. So Wayne, how about this one?
Well, Triv. It's kind of similar to the other ones. But this is replaced by the OH minus. It's kind of similar as in you can see what's going on. This is going to replace this. So you basically get the same thing but with an OH at the end. It won't be negative when it's bonded, that's why it wants to bond. Then you produce a Br minus ion. Again, we do this actual mechanism, but this is in part 3, it's earlier in the book.
It is earlier
so
in
it's
the book.
earlier in our videos, part 3.
So then a second, and there's another one, and that's
Elimination. I
Yeah.
was going to say termination, that's not it. So,
Okay, right. So elimination's a bit different when something is
broken down by
broken
an acid.
down. Yeah. So we start with something and we change it to something else. So if we have,
C to OH.
alright, we'll have an alcohol,
We have an acid catalyst.
Yeah.
So we'll just put acid.
and
That
well,
breaks down and puts a double bond into it, like this, and produces water. Quite simply, like that.
yeah,
This double bond will take away 2 things. If it takes away this, then it will also take away the H, and it will take away another hydrogen. You should see that
Yeah.
will make
for
water.
the double bond.
Then we just get what we started with up here. So
We do, so
if we
full
do
circle.
this, and then add bromine, you can do circles. And you need to appreciate this to be able to really understand it in your exams.
Yeah.
Getting from one thing to the other, and then what can you do to the thing that you've made, and what can you do?
Yeah, there's so many pathways to get from one thing to the other, and you have to know loads.
Yes. We don't do a mechanism for this is just something you need to know, but we will
It
do
is.
these as we said, part 3, part 4. If you're confused about the mechanisms, go to those videos now.
Yeah, but first, got a bit of revision about GCSE.
Percentage yield.
Yeah, I mentioned it. We did mention GCSE. And believe you never get 100% yield.
Well, you very rarely do, Triv. When you react two things together, you often make more than one thing, but you only want one of those
them,
things.
yeah.
So you won't have 100% percentage yield.
What you can get is 100% atom economy.
Now that takes into account how you use the thing. So you might make the thing you're trying to make.
And then the waste thing, or what normally be a waste thing, you use it to make
for
something else. Yeah.
So you might have 100% atom economy. Like in a lot of reactions, CO2 is produced, and we're now finding ways to then use that CO2 to our benefit,
Yeah.
increasing atom economy. Percentage yield would stay the same.
It would.
So that's revision from GCSE.
It is, and I think we're on to a bit more as
Yeah.
well. The uses of hydrocarbons.
Yes, let's do that. Hydrocarbons.
Oh.
Right. So, hydrocarbons, they come from crude oil, as you should know from GCSE.
They do. I need to know a bit about them before we go into their uses.
You do. So we have a fractional distillation column.
We do. So, we're just running through how it will work. You should know from GCSE. Crude oil goes in there, gets heated up through these things.
This is like a big furnace here.
Yep.
It goes in here.
And it splits due to its different boiling points. We should know something about crude oil. It's a mixture.
Yes, there is lots and lots of hydrocarbons in crude oil.
Yep. And they all have different boiling
A lot of
points.
different boiling points. So this is hot, this is really good. It's about 20 degrees, this could be up to 400.
Yep. So, you don't need to know what they all are.
No.
It's useful to know it right at the bottom. It's bitumen.
Bitumen,
Top, petroleum gas, and in the middle, kerosene.
diesel, then a bit above it, kerosene, then stuff that's used for ships like the oils and
Yeah.
stuff there.
And that's about that.
But you need to know how it's done and how it goes up.
But mostly you just need to know the boiling points and
Yes.
why they differ. So, this is the main part.
We have. I'll just do a simple alkane. No.
Alright.
I know it's skeletal. You know about skeletal. don't you?
Yeah, skeletal's much, much easier. There we go.
Right.
Beautiful.
We have a nice alkane like this
Yeah.
compared to
Little
a
alkane.
small one. Which one has the highest boiling point, Triv?
Well, it'll be this one.
It will be that one. Revision from your Unit 1 chemistry. This will have more van der Waals forces.
Because it has just so many more electrons, so many more chances for induced.
Because of these extra forces, it takes more energy to break, hence more temperature, because the temperature is essentially energy.
Yeah.
So it'll take more energy to break this than this. What about if we rub this off, Triv?
Okay.
And this has got 1, 2, 3, 4, 5, 6, 7, 8 carbons.
Okay.
1, 2, 3, 4, 5, 6, 7, 8. So I've got some branching.
We
That's
have
the
got
same number of
branches.
carbons. What happens there?
Well, with this isomer, because it's an isomer,
This is an isomer. We just did this.
this also has lower boiling point.
Yes.
And that's because
These different side chains repel each other more.
They
These
do.
all have hydrogens coming off,
So
they all
it's
repel.
much easier to remove them, so you need less heat.
Yes, and they
or
have
less
much
energy.
less van der Waals forces. They don't have the same number, which is a common misconception. Because of the repellment, they have less.
Yes.
Now we've done this, we can actually go on to the uses, and in particular, the use as fuel, which is his major use.
Alright, so let's crack on to that now.
Crack.
Hello.
On to hydrocarbons being used as fuels now.
Yeah. So, do you know how engines work?
Yep, we use alkanes.
We do.
So I'll use a simple one. This may not necessarily be the one that's actually we use the one that's used in petrol as octane,
Alright.
which is C8H 2N plus 2 18.
And we burn that.
But
It uses oxygen. And, well, sometimes it completely combusts, which means that it will form carbon dioxide
and water.
and water, but doesn't always.
Sometimes this will burn inefficiently.
Yeah, it will do something called incomplete combustion.
You still write it like this.
Yeah, but it makes carbon monoxide,
and water.
which is not so handy.
It's not so handy. I haven't balanced this equation, and I'm not going to, because it's just the idea that's important. In internal combustion engines, some of this is done, but really it's mostly this that's done, unfortunately, especially with long distance travelling, the more of this that's done. Unfortunately, it's just the way our combustion engines work, what with all the heat and stuff, and the fast movements.
Yeah.
It's hard to get plentiful supply of oxygen into the engine. And this isn't good. This is
No.
We'll go on to this more in a minute. but this is not a good idea. But you just need to appreciate that this is what happens in a combustion engine, and that both of these can happen.
Alright, so let's crack on to cracking.
Yep. Now, cracking uses from an idea from fractional distillation, the next part.
So, in fractional distillation, you make quite a lot of all the things.
Yes.
But there's a much higher demand for stuff, short chains.
Yes.
There's
Like
lots of
the big stuff like bitumen, you don't need so much of that at
No.
all. Fuel is much more important.
It is. But to counteract that high demand for one thing and low demand for the long chains, we split them up.
We do.
And we call it cracking.
We call it cracking. I'm not going to put up an example because I don't know the different things that can be formed. There's many different things that can be formed, is what I'm trying to say. But you take a big alkane and you break it up into a little alkane and an alkene.
Yeah.
And there's many different things you can make. You can make this size alkane and this size alkene, or you can make this size alkane and this size alkene.
And it goes on.
You don't know exactly what to do, so that's why I'm not going to write it up.
Yeah.
The idea is important though, cracking.
It is. Lots of ideas in this chapter.
Yes. The next idea, again, is to do with cracking.
It is, and it's reforming.
Yes. When you make a shorter chain alkane,
It burns quicker.
it burns quite quickly. Which you want it to burn, sure, but you want it to burn as efficiently as you can.
Yeah.
Because, as you'll know, it's from a finite source, but it's in huge demand. So we want it to make it last as long as possible. We do this
You turn it into cyclics.
Yes, so if I use pentane, this one I can write an equation for.
So
C5
H2
H2N plus 2.
So 12.
This gets reformed.
We don't need to know the entire mechanism, but it gets reformed and it gets turned into cyclopentane.
C5
But
H10
we should realise that as you go around in the circle,
Yeah,
is it hydrogen's
I'll
lost?
draw it. We've got 1,
Oh.
2, 3, 4, 5. And that will go to 1, 2, 3, 4, 5. I always get confused with shapes. Plus a hydrogen, which you can't draw in skeletal because
You can't.
hydrogen is ignored by skeletal. But it does that, it creates a cyclic, and it's important to know that this is more efficient in an engine. It's normally one mark in a question combined with the rest of this sort of stuff.
Yeah, they're all very big questions.
Yep, like this might be one mark to do something like this, and then it might say it's actually incomplete, or how does this change it? And you might need to know.
And then you do that bit.
The idea that this burns better is important.
Yeah, and then this bit, next bit is about more wordy questions.
Yes, and less fun to do, I suppose, but you need to know.
There's,
Should be ideas from GCSE,
Should
doesn't
be.
develop much.
and it's biofuels.
Yes, the idea of what's the difference, well not what's the difference, what's better about biofuels than normal fuels, our petrol and stuff.
Normal fuels are really good, but we're running out.
We are running out. And they produce CO, which is a poisonous toxic gas. They produce CO2, which is a greenhouse gas. They can
Yes,
make
something.
nitrogen oxides and sulfur oxides, which are harmful to the environment and can cause acid rain and stuff like that. There's lots of problems affiliated with what's produced, basically.
Yeah. And biofuels, you can grow something, you can grow sugars, which you can
Grow
ferment
sugars.
into ethanol, which burns pretty well as well.
It's just as good as this, and it's nowhere near as polluting.
The only problem is big fields full of that instead of food.
Yeah,
Little problem.
this is all revision from GCSE. You should have had massive debates about this at GCSE. Should we use biofuel? Should we use this? Not much to develop really, that's about
just it.
But that actually concludes part 2.
It does.
Part 3, we go on to the mechanisms of what we've done with this video.
We do, which is a bit more complicated and a bit more interesting.
Yeah, let's crack on to that.
Alright. Now I've finished cracking on about cracking, let's crack on and do something else.